That's the clap for cutting later. Hello, welcome to the August 2021 meeting of the Forth2020 Facebook group. I'm happy that we have lots of people joining us, and we have interesting talks about Forth, of course. And our first speaker will be John Hardy. And he's talking about a Forth threading strategy on the Z80 or Z80. Let me know what the right pronunciation is. I know this is probably a British US thing. Okay.
It's Z80. It's Z80.
Right. Right. Okay. Yeah, please go ahead.
Okay. Thanks. Thanks, Ulrich. Yeah. I'll just share my screen. Hopefully this works. And can everyone see the screen? Yep, cool. All right. Okay, so I thought I'd just introduce myself. I've been involved in with the Z80 for 40 odd years. Since the late 70s, in fact. In 1983, my friend Ken Stone and I published a computer kit called the Tech One, which was based on the Z80, and it was a popular kit in Australia. So quite a few people built it and got their first experience of programming microprocessors and that sort of thing using this one. In fact, it was many people's first computers that told me that since that. And we started a Facebook group about 2 years ago. I've been sort of coming back to the Z80 a little bit because I've since then had a career as a software engineer. And in that same period, in the 80s, I first became acquainted with Forth. I read Leo Brody's book and generally admired it, but didn't have working versions of Forth until more recently. When I was starting to look at projects to do with my Z80 in relationship to the Tech One Z80 group on Facebook, I started to think about Forth again, and because the main problem with the Tech One was it was a great electronics kit, but it wasn't a terribly good environment to program because it was a simple hex pad type arrangement. So since then, I've been working with group members, and we've basically got a serial interface happening for the original board, and of course we've got successor boards also being made. This is the point. This kit is still being made, nearly 40 years later. So, of course, you don't want to do basic. Some people already have done basic. We don't want to just repeat the whole, that cycle. I thought Forth is a much more interesting language to do because it fits into the assembly language mindset. If you've been programming a Z80 in machine code, programming in Forth is actually a breath of fresh air. But it's still got that something about it that I really love about assembly language, and I also love about Forth. So there's just something about the aesthetic of Forth that I particularly like, and it actually makes assembly language programming so much simpler if you start using Forth techniques. So I've been working on Forths in various forms over the last 2 to 3 years. I just went into it boots and all, not really knowing how to make the fastest Forth for a Z80. This is by no means the first Forth for the Z80. There are many. So I've been studying all of them, in particular Camel Forth, eForth, and various other implementations of Forth for the Z80. So the questions are, why am I even doing this? Well, because it's retro computing. You don't ask why. It's the art of it. It's the enjoyment. It's the limitations. It's all of these things are part of it. But nevertheless, we're still interested in performance and efficiency. In fact, you know, these are very interesting challenges in the 8-bit world. So, and that said, you know, the Z80 is probably a little bit under spec for Forth. Forth is better on a 16-bit processor as a minimum, but, you know, getting things working on 8-bit is still a lot of fun. So as I say, the main thing is, are there any improvements that can happen? This is a very well-trodden path. The Z80 is one of the original chips that people implemented, the first widespread Forths. So the questions I have are whether there's anything left in the tank. Just to remind people, because I know a lot of people started on the Z80, but they might not have thought about it very much in more recent years. This is the general layout. We basically have 3 sets of, we've got 3 register pairs that are most used for Forth. That's BC, DE, and HL. We also have an alternative set, but they're kind of a little bit hard to get access to efficiently. So they tend not to be so easily used. They're more a good idea on the drawing board than an actually very useful feature of the Z80. That goes for the index registers IX and IY as well. They're somewhat more useful, but they're kind of slow compared to the normal register pairs. So a couple of things when I started implementing my first Forth was to follow some of the advice that I saw, which was to keep the top of stack in a register. And this is an obvious optimization because so many operations just work on the top of the stack, and therefore it's a worthwhile optimization. I did look into also the idea of using the second to the top of stack as well, but that didn't really work out. So essentially, you know, that's a worthwhile thing to do. So I set, in my particular Forth, I'm using DE as the top of stack. The other interesting thing about Forth when implementing on an 8-bit microprocessor is that it's 2-stack architecture. This is problematic because Z80 only has 1 stack. Unlike, say, the 6809, the single stack architecture means at least 1 stack is going to need to be implemented in software. So, you know, it's going to need some kind of push and poke and or push and pop. And if we assume here that BC is the stack pointer that we're talking about, this is going to be a slow stack compared to the normal machine stack, the normal return stack that the Z80 uses, because the Z80 doesn't have any 16-bit indexed address operations. So you have to break them down into chunks of 8-bit. So a software stack is going to be somewhere between 3 and 4 times slower than the built-in machine stack. That which then raises the issue: what stack should be used? Initially, in my first version of Forth, I just could not bring myself to use the built-in return stack as the data stack. It just did my head in too much. But I've come to realize that the data stack is so important and so critical, it needs to be the fastest. So therefore, I've used the return stack, the built-in machine stack, as the data stack, and implemented the return stack in software because the return stack is used less frequently than the data stack. So it's just a sacrifice that you have to make. So that's fine, except that rapidly starts to complicate the way you program. It means that subroutines don't work quite the way they used to work in a normal way, because you're essentially, when you make a subroutine call, you need to push the return result onto the stack. And the problem is that stack's already been used as a data stack. So before you can start accessing those values, the normal data stack values, you've got to do something about that return address because it's sitting there right at the top of the stack. But these things are actually quite easy to handle. But therefore need to start thinking about these things. So that's where we get to the topic of the talk. It's heavily influenced by a paper or a series of articles written by Brad Rodriguez, which I'm sure many of you have read, which is called Moving Forth. And it's a series of, I think, 4 or more articles about basically implementing Forth on 8-bit microprocessors. And he covers the whole range from 6502s through to, to Z80s and so on. And it's even if you've read it before, it's always, I find it a good one to go back to. It's just one of those things. So there are a number of threading models, token threaded, and which is topic of, I know Ken Bogue has been talking a lot about token threaded forths. Is one model, but indirect threaded, direct threaded, subroutine threaded are the ones that I'm going to be talking about in this talk. Also ITC, indirect threaded, is quite similar to direct threaded. So I'm actually going to skip that and just talk about direct threaded forths and subroutine threaded forths. So just as a recurring sample, I'm just going to use this example of a colon word, a word that is essentially made up of other words. Its name is double. It has a single, it basically doubles the value that's on the top of the stack. So it does that by duplicating the top of the stack and then adding those 2 items together. A very simple example, which everyone comes across in their first learning of Forth. So you put 3 on the stack, call double, and you get 6. So direct threading, all definitions, they're slightly different to indirect threading, but I won't go into indirect threading. All definitions are machine code. In other words, they all start with the machine executing in the word itself. So in the case of a primitive words are those ones that you use all the time that you build up from. They don't call other words. That's why therefore I'll call them primitives, are just pure machine code. But we need to end that machine code, not with a return, but with a piece of code which we call next. This is a repeated piece of code, which is usually done as a macro. It could also be done as a subroutine, but essentially it needs to clean up and deal with the fact that the stack is not a normal stack. The other kind of word is a colon definition, which in the case of our word double is a series of calls to more primitive words like dupe and plus. And they always end with an exit, which is another word, which basically transfers control to the next thing. So next in the Z80 is basically a case of in direct threaded and indirect threaded, you need to have in one of the registers a pointer pointing to the next word. And essentially what next does is it uses that pointer to pick up the code for the address for the following word and put it into its own registers and advance it itself. And it's kind of clever enough to advance the pointer as well. So it's now pointing at the following word. It's basically like a program counter in a normal machine code context, but this is an emulated virtual machine kind of thing. And that's because we've had to go into this kind of world because of the use of our threading and the use of our stack in this way. The main things that I'm interested in here is how slow these things are. So you can see that the overhead of this particular operation is 55 T cycles on the Z80. A T cycle is essentially 1 T cycle at 1 megahertz is 1 microsecond. So that means we've got 55 microseconds just for this particular operation. You can see that primitives all take the form of some kind of work that happens. I've actually forgotten to mention the register pair in that push operation, but basically the duplication is pushing the content of a register pair, in this case DE, onto the stack, and the drop operation is popping it back into DE. DE is the top of stack. I forgot that in this particular slide. And colon definitions need to have some additional stuff. They need to push their return address onto the fourth return stack. Then they call this same bit of code called next. Then they do whatever they need to do inside that word, and then they need to exit the same kind of way. Oh, this will make sense, but I mean, the main thing is, I think most people are probably familiar with this scheme. The bit that is interesting from my point of view is how long these take on the Z80. This is a typical example of a colon word written using a direct threaded model. The first thing that happens when you enter, as I mentioned before, the machine code, each word definition is machine code. So it has to first go off and call a generic piece of code called enter. And then it has a data, essentially a list of references that follows it, which essentially represent the fourth program, dupe plus exit. Where I've gone with this is essentially to build up or calculate essentially the overhead that is being applied to the program and doing it on sort of a weighted basis based on the proportions and percentages of these different words. So things like dupe appear all the time, whereas other words might be quite infrequent. And essentially this would be, and this is what gets added to the total operation of a typical piece of source code. So this is based on a piece of source code. I've just basically done a frequency analysis of it. I haven't shared the spreadsheet itself. This is just summary data. And this is just an initial step to give you an idea of where I'm going with this. The main point is that these numbers, 32,000, we want them to be smaller because they represent the overhead. And we're trying to get that as small as we can. So borrowing from the carpenter's phrase of measuring twice and cutting once, we're going to code once based on measurement. This, I wish I'd followed this advice before I started my first Forth, which of course I didn't. I just launched straight into it. And this time round, I'm measuring everything before I do any implementation to try and get the fastest architecture going. And of course, implementation has been going on since then. But these are the findings. So before we get into that, I want to talk about the alternative to direct threaded code, which is subroutine threaded. The difference between direct threaded and subroutine threaded is that you don't need an inner interpreter anymore. You're essentially just representing the fourth word, colon word, as a normal piece of machine code, which is making a series of calls directly to the words that you're interested in. So we have, this obviously simplifies the model. It frees up one of the register pairs, and as you can see, they're in short supply. So one free register pair. We don't need the IP register anymore. We can just use the program counter of the processor. We don't need to have next at the end of every operation, which reduces the overhead of enter and exit as well. It could be faster. We need to find that out. It's going to be bigger. And that's probably one of the that is the major downside of subroutine threaded, and why people don't usually do it on 8-bit microprocessors is because you're suddenly turning a 2-byte reference into a 3-byte reference because it includes the call opcode in addition. So suddenly you end up with 3 bytes. It also we also need to deal with the fact that now this data stack is really going to get starting to be used as a return stack. So we better start, uncomplicating our life a little bit with regard to that. So here on the right, you can see an example of what I'm talking about. Basically, call over, call cat, call XOR, and drop over, etc. This kind of thing with a series of calls is how subroutine threaded Forth looks like in Z80 assembly language. I'll just quickly summarize what registers I ended up using. The stack pointer is now the data pointer. The BC register is now the return stack pointer. DE register pair is the top of stack. And IX is a temporary variable that I use. HL and A, the traditional accumulator, are kept free to be used for transient values. And I don't make any heavy use of the alternative A register, the IY register, or the alternative BC, DE, and HL registers, but I leave the option open that I might be able to find a useful way to use those. So the big issue is because you're making calls, you're pushing that return stack onto the data stack, which you're pushing that return address onto the data stack. This is just something that we don't want to leave around because it makes it hard to read the data stack. So for colon definitions, we need to transfer that address from the data stack to the Forth return stack as the first thing we do. That's the equivalent of enter colon type macro. In primitives, we don't need to go the whole distance of transferring that return address onto the return stack. We can just store it in a temporary location. So where I'm putting it is in the IX register. So I pop it off the data stack and I put it in IX, and then I use it again later. And that's fine for primitives because primitives don't call other Forth words. So that doesn't need a recursive sort of approach. You can call other machine code, but it just will not have quite as clean an interface to the data stack anymore, but you can do that. So we've got different enters and exits. When entering a primitive, we just pop the return address straight into the IX register and just leave it there because IX is not used for anything else. And then on leaving, we just jump to the IX register. In the case of colon definitions, we pop it into HL because it's more useful there, and then we push it onto the software implemented return stack, the Forth return stack. And the opposite routine, when we leave it exit colon, we just pop it and then we jump to it. So you can see that this adds essentially 38. That's actually miscalculation on that second one. It's actually 17 plus 44 plus 38. But anyway, I've got the numbers wrong on that second one. It's closer to 100. So, so here's an examples of what the code will look like. Enter prim, push DE, exit prim, and then drop, and so on and so forth. This is how you would implement primitives, dupe and drop. This is how you would implement double, which is a colon definition. We go enter colon, then we call dupe, then we call plus, then we call exit colon. Comparing DTC, you can see there's some inelegance with this, and it does use more memory. But we can see that we are getting a 25% drop in the overhead of the word. And that means on all words, it's going to be, possibly, 50% faster to implement, to execute that overhead code than it would be. And so with a distribution of prims to colons, I've got slightly different values for when it's very primitive heavy versus where it's very colon heavy. But essentially, you're seeing a pretty consistent saving of around 30% of the overhead. So it's a trade-off. One of the things about this table is it also talks about how much bigger your code is going to be. It's going to be 50% bigger. That's the downside. So you'd want an improvement in the speed for that. It's a trade-off between size and speed. STC consumes 50% more memory, which is very significant in 8-bit systems. STC is about 25 to 30% less overhead. The advantage grows as a percentage of colons relative to primitives increases. But wait, there's more. One thing that STC really gives you that makes it worth even talking about is the fact that you can inline definitions directly into the word so that you can actually just expand it, treat the word like a macro rather than treating it like a subroutine. The problem with that, of course, is it's going to expand your code even more if not done carefully. So it's a no-brainer for any kind of operation which takes less than 3 bytes, of which there are a few, like, for example, dupe and drop can be implemented in 1 byte. And it gets rid of 100% of your overhead. So while it increases, it can potentially increase your code more than 50%. And it also makes code inspection like C harder to see the definitions. I'm calling it STCI just for inline. And both size and speed are quantities that you want to optimize. You want to inline all of your really short operations, anything less than or equal to 3 bytes, no problem. And also you want to inline the most common short operations. But everything else you should do as a subroutine call. So this is an example of what the code would look like on the right-hand side, full of inline code. And it starts to look a little bit more like native compiled machine code. So these are some of the candidate words that I would inline, the ones that are most common and the ones that are the shortest. And you can see that, like, if I inline dupe, it could actually make my code smaller, but most of them increase the size of the code a little bit. And without inlining more than these really, really common ones, you can see that, like, these are hugely common: dupe, swap, over, rote. Rote's a little bit controversial because it's 6 bytes in size. Drop, minus, here, plus, character fetch, etc. These are all being done as inline. And this is to give you an idea what the code would look like for some of the most common operations. And comparing, we're getting to the business end of it. Basically, it does make your code larger, around 65 or 57% as opposed to 50%, but it does make your code faster by reducing the overhead by at least 50, in the order of 50%. So you're getting a significant, but not slam dunk. It's really got it needs to then be seen whether it's worth it, this kind of reduction in overhead. But more size gives you more speed up to a point. We need to, I basically see this as a job to optimize this further to get an optimum sort of value for this. 50 to 60% increase in size over DTC, 45 to 55% less overhead when compared to DTC. The generated code looks more like native code, easier to integrate with your other code. It's essentially a compiler, basically. It's compiling in the same way as a C compiler, but the good thing is it's Forth, so it's actually smaller and neater than the C compiler, less like a virtual machine, and reduces the overhead of loops and branches because they can be implemented as native. So my final conclusion is that DTC remains the best all-round solution. It's what Camel Forth is written in. It's what eForth is written in. And it still would be probably the most recommended. However, if you do want to experiment with the idea of getting that extra performance at the cost of a little bit more memory consumption, then DTC is worth doing. And that was not obvious to me before I started this. So it really was an exploration that had to be based on measurement. So STC and STCI have significant benefits, and they reduce the overheads on every word, and this can speed up Forth considerably. Commonly, inline sequences should be kept short. Finding the optimum compromise between size and speed still needs more investigation. So this is examples of my Forths. The one I wrote 2 years ago is called Firth, as in the Firth of Forth, which is a bridge area in Scotland. There's a great interview with Charles Moore in front of the Firth of Forth. And Z Forth is the one that I'm working on now. So in answer to Ulrich's question, it's Z Forth. And I'm still in the process of implementing that. But anyway, the only way to know for sure is to write sample code. That's one of the mantras in Brad Rodriguez's Moving Forth. And so that's my discovery based on measurements. And that's it. Thank you.